Hello everyone. So today we are going to do the Thevenin's theorem. So this is the second topic of this particular module, that is the DC network theorem. So in the last class, what we have done? We have done the superposition theorem. So in superposition theorem, we have what we have seen. So we have seen that how we can solve the superposition theorem. What are the conditions to apply the superposition theorem? The steps how we can solve the superposition theorem, and what is the limitations of superposition theorem. So there we have seen some conditions, steps to solve. So like that, with the same procedure we will follow for this particular theorem, that is the Thevenin's theorem. So in this theorem, so first we will see where we can use this theorem, when we can use this theorem, what the steps to solve the theorem, what is the utility of this theorem, and if there is any limitations of the theorem. So first, concept, why we are going to use this theorem. Say we have a big large circuit, so 4 or 5 loops are there. So now we want to find out some current passing through some particular branch. So what we'll do, if what with the basic concept we have the concept of KVL, KCL. So what we'll do, we will to make loops, we will solve the loops current, and then suppose say in the fifth loop we have to current the find out the current. So 5 times you have to make the loop, so five equation you have to make the 5 equation you have to solve. So after solving 5 equation we will get the result. So the procedure is very lengthy. So how we can reduce that? So we can reduce that if we use this Thevenin's theorem. So in Thevenin's theorem, what we can do, that is, we can find out the current passing through any particular branch of a complex circuit. Complex means a larger one. Okay, and remaining all resistor, all the component sources remaining constant in a particular circuit. If a particular resistance value is changing continuously, then also we can apply this Thevenin theorem. Okay, so coming to the statement, so what is told over there, any complicated network across its load terminal can be substituted by a voltage source with one resistance in series. This problem helps in the study of the variation of the current in a particular branch when the resistance of the branch is varied. I have already told that one, while the remaining network remains the same for example designing of the electronic circuit. Remember the point. So application wise, this theorem can be applied in the electronic circuit, where a little change in circuit parameter, that means the value of the resistance, little change in resistance will make some little change in the current value, and that can operate some larger device. That means that is switch on or switch off some larger device which has higher current rating or voltage rating. Okay, so the basic concept is that we will reduce a complex circuit, a simpler one, where it will contain only a equivalent voltage source, a equivalent resistance, and the load resistance. So for simplicity, I am just giving you an example. So for your understanding, I have considered here a circuit, so which containing a Vs source, supply voltage, R1, R2, and R3 resistor in the circuit, and there is a load resistance RL, through which our current is flowing, that is IL. Okay, now we want to find out that through this RL, that is load resistance, how much current is flowing. Okay, so that will be our aim. Actually, we the same example I have taken in the latter one, when we are going to solve step by step how we can solve. So just for your pictorial representation, for your simple understanding, so say this is a circuit and our aim, just take this in your mind, that our aim is to find out the current passing through this RL, that is IL. Okay, so up to now just remember this one. Next, use. So as I have told already that this theorem can be used to reduce a complex circuit to simpler series circuit, which will contain a equivalent voltage source, equivalent resistance, and the load resistance all are connected in series. So we will going to see how we are going to do. And it is a second point use, it is a voltage equivalent theorem. So yes, it is a voltage equivalent theorem. Why? See what we are doing. There is a large circuit, we are reducing that circuit a smaller one. So when we are reducing the circuit in the smaller one, so we are considering that at that time in the circuit we have a equivalent voltage. Okay, correct. So as we are assuming that in the circuit we have an equivalent voltage, so that's why we can say that this is a voltage equivalent theorem. Okay, so in the next theorem, in the next part of this Thevenin theorem, we have a Norton theorem. So there we can find out that, so that theorem is actually the current equivalent theorem, because at that circuit we are going to reduce the circuit to a simple parallel circuit which will going to contain a current source, equivalent resistance and load resistance connected in parallel. Okay, so that we will do the later. So for now, just remember that Thevenin's theorem is a voltage equivalent theorem. Okay, so this is important for objective also. Okay, terms to know. So that is we have already done in superposition theorems also. So what we can see over here, so the first point is, so the components in the circuit must be linear, correct? So linear means already we have discussed, that means, so here what I have taken, I have taken the left hand side, I have taken the original view of a register, and the right hand side I have taken the symbolic representation of a register. So for your understanding, just say, so in the right hand side the resistor is there. Now there is the two terminal, left hand side and right hand side. So if we connect in the left hand side source, then what will happen? Current will flow from left to right, or like this way, vice versa. So current will flow if we will connect a voltage source, so current will flow. The point is, if we increase, say for your simplicity, say 10 volt source is, so 10 volt supply is connected to the resistor. Now what will happen? So say 0.1 ampere current is flowing. Now if we increase the voltage source, say from 10 volt, we have increased the voltage value to 20 volt. So what will happen? Definitely what you can understand, the current value will definitely increase. So my point is, if voltage value is increasing, then through the resistor current value will increase. If voltage value is decreasing, through the resistor current value will decrease. And the element which has this property, that means linear VI characteristics, if voltage is increasing, current will increase. If voltage is decreasing, current will decrease. This property is known as the linear property, which follows the straight line equation, y is equal to mx plus c. So a circuit which contains this type of element is a linear circuit, and we have to remember that in a linear circuit we can apply this Thevenin's theorem, correct? Number two, all components must be bilateral. So bi means both. So here what we are going to do, what we have to understand that, so in the right hand side we have the symbol of the resistor. So now just assume in the left hand side, if we connect a source, so current will flow from left side to right side. Now assume again in the right hand side, if we connect the source, so what will happen? The current will flow from right hand side to left hand side. So that means, so according to the potential, current will flow from through the both direction of the material. That means if we through this resistor both direction current can flow, and an element through which both direction current can flow is known as a bilateral element. So a circuit which contains bilateral element is a bilateral circuit, and as per the theorem, this theorem can be applied where bilateral circuit is there. Okay, so in one word we can say bilateral means both direction current can flow. Okay. Okay, passive components may be used, resistor, inductor, capacitor, or the passive components. Okay, now explanation, the main part of this one, explanation of the Thevenin's theorem. So what is the explanation of the Thevenin's theorem? So I have considered here a circuit as we have already discussed that this is the circuit. A voltage source is there, Vs. There is the R1, R2, R3, three circuit resistors are there, and there is a load resistance RL. And we are assuming that through RL a current IL is flowing. Okay. Now, what are the steps to follow? So to understand, just coming to the next diagram. See. So as per this theorem, it is told that the we have to remove the resistor from the circuit through which we have to find out the current or voltage. Okay, that means load resistance we have to remove from the circuit, make that terminal open, and find out what is the voltage value at that open terminal. Correct. So what points to remember? First, remove the load resistance. Number two, make that terminal open. And number three, find out what is the voltage value of that open terminal. So these are the three things you have to do. Again, I am going to tell you. So first, remove the load resistance. Number two, make that terminal open. And number three, find out what is the voltage value in the open terminal. Okay. Now, if I ask you what is the voltage of the open terminal, see, as we can see, just take a look in the diagram and the pointer I am discussing over here. See, this is the voltage source Vs. So current will produce from here. So it will go like this through R1. It will go to this node. Then it has two way to go. One through this one it can go. This one it can go. Okay, but it will go to this direction. No, is it go? No, through the R2 because there is open terminal and already we have discussed that open terminal always give us the infinite resistance. So as we know, through infinite resistance no current can flow. So current cannot flow through this path. Current cannot flow through this path. So what will happen? Whatever current is coming through this source, it will it will flow through R1. This coming to node, it will flow through R3 and returning back to the source. So this is your loop. So is there any current in R2? No. So if there is no current in the R2, so what will be the voltage value? So we can say that actually there is no voltage in AB. But if we connect some voltmeter over there, we will get some voltage over there. So where we are getting this voltage? Actually, this voltage is the voltage drop of across R3. See, whatever voltage drop will appear through this R3, that will appear across AB terminal. So if we want to find out what is the voltage across AB terminal, that is the open terminal of this particular circuit, so what we have to do, we have to find out what is the voltage drop across R3, and that voltage drop across R3 will give us the open terminal voltage, and that particular open terminal voltage is known as Thevenin's voltage, VTH. Thevenin's voltage, V suffix TH. So what is the voltage across R3? So we know from the Ohm's law the voltage drop across R3 is equal to the current passing through this R3 and the resistor value of this one. So we are assuming that the current passing through this R3 is I. So I into R3 will give us the voltage drop across this R3, and that will be our VTH, Thevenin's voltage across the open terminal. So what is I? I means we know that in this loop, again Ohm's law, V by R. V means this Vs, and R means this two resistors are connected in series because there is no current division at this node. So we can say that, see, coming to the formula, VOC, open circuit voltage, is equal to I into R3, as I have told, this I into R3 is equal to, now what is I? I already have told, Ohm's law, Vs by R1 plus R3. So Vs by R1 plus R3 into R3. So that will give us the open terminal voltage, that is our VTH. So first step is done. So this is our equivalent resistance for this particular circuit. So remember this point. Say I have taken an example of a circuit which has two loops, correct? Now it may happen you will get a circuit which contains 3, 4, 5, 6 and numbers of loops, and you have to find out in the voltage across or current across a particular resistor. So at that time what we're going to do, the same procedure we're going to maintain. What is the procedure? So it will be asked that through that particular resistance you have to find out some current value or resistor voltage value. So as per the theorem you will go, you will remove that particular resistor from the circuit, and you will find out that across that open terminal how much voltage is appearing, and that voltage will give us the equivalent voltage or voltage source of this Thevenin theorem. So simple. So remove load resistance, make the terminal open and find out across that open terminal what is the voltage. So that will be our equivalent voltage source. Now coming to the step 2. See what I have told, that is already written over here. This is VOC, also known as Thevenin's voltage. So number 2, step 2. So step 2, it is told that make this circuit, make this whatever circuit is given to you. So first, in the first step, what we have done, so we have removed the load resistance, we have made the terminal open, and we have finded out the open terminal voltage. Now what is the rule for the second step? So in the second step what we have to do, it is told that make the circuit independent of any kind of source and view from the open terminal and find out what is the equivalent resistance of the circuit. So two things we have to do. First, we have to make the circuit independent of source. May circuit may contain the voltage source or current source. So we have to remove all. Okay, whatever is the source. So as we know that when we have to remove voltage source, we have to make that terminal short. We have to remove current source. We have to make that terminal open. Correct. So we will go like that way. And second point is that we have to view from the open terminal from where we have removed the load resistance. So we will view from that terminal and we will find out what is the um, equivalent resistance of the circuit. Okay, so here also we have done the same thing. See here, there is the Vs, there is the voltage source. So when we will remove this Vs, we will make that terminal short. Correct. So we have done this one. So we have removed Vs from here and we have made this terminal short. Now view from this open terminal. View from this open terminal means like that. See, we can think like that way. See, if some current is flowing through this path from this open terminal, then how the current will distribute it in the circuit. So how the current will distribute in the circuit, as per that division, current division, we have to assume the series parallel combination of the resistance. Correct. So if we think that there is a current is flowing through first R2, so at this node it will divide between this R1 and R3. So what we can say, this R1 and R3 both are parallel in combination, and with that this R2 in series. See, this is, it is written over here. So R2 in series with this R1 R3 parallel. Okay, and that particular equivalent resistance is known as Thevenin's resistance. Okay, so in the first step what we have done, we have simplified the circuit, we have find out equivalent voltage source. Next we have what we have done, we have removed all the sources from the circuit, we have viewed from the open terminal, and we have find it out what is the equivalent resistance of the circuit. Okay, so that is known as the VTH. Now coming to the last step. So last step, as the theorem states, that we have to make a simplified series circuit. So what is the simplified series circuit? There should be a equivalent voltage source, there should be equivalent resistance. And initially from the circuit, what we have disconnected, we have disconnected the load resistance RL. See, in the diagram we can see that. So first step we have find it out this VTH, second step we have find it out this RTH, and initially we have disconnected this RL from the circuit. So connect all these three components in series, correct? So connect all these three components in series. And now if I say you find out what is the current passing through this RL, you can easily find out. Why? Because this is a simple series loop, and in the simple series loop we can very easily apply the Ohm's law. So what is Ohm's law? V is equal to IR. Now what we want to find out, I means, that means B by R. So what is V over here? This VTH is a V over here, and what is R over here? This combination of this RTH plus RL is the total R over here, because both are in series. See, so that is actually written over here. IL is equal to VTH by RTH plus RL. Okay, so that means, so if we summarize what we have done, so we can find out, we can say that whatever is the circuit, whatever complex is the circuit one, so we can reduce this circuit to a simple series circuit which will going to contain VTH, RTH and RL, correct? So this is all about the Thevenin's theorem. So points to remember, that where we can use this theorem, how we can solve this theorem, how we can reduce the circuit to simple series one, simple series circuit. Okay. mm, okay, so VT chart is whatever I have told. Okay, so for your better understanding, what I have given over here, what is the steps, what are the steps I have told. So first you have to remove the RL. Next, we have to find out the open terminal voltage. Next we have to find out the RTH of the circuit, that is after removing all the source from the circuit, we have to view from the open terminal, and we have to find out the equivalent resistance, that is known as the Thevenin's resistance of the circuit. And we have to make, in the last case, we have to make a new simple series circuit which will contain VTH, RTH and RL all connected in series, and find out the series current, that is our load current. Okay, so this is all about the theorem that we have discussed. Thank you.